Hello students, welcome to the concept relation between directivity and maximum effective aperture. The last video I explained about maximum effective aperture. Maximum effective aperture is related to the power that the antenna can receive. If the effective aperture is more, the power received by the receiving antenna will be more. Okay. So now in this class I want to explain the relation between directivity and maximum effective aperture. For that, consider two antennas. Yes, this is one antenna and this is another antenna. One is the transmitting antenna. The first case, consider the first antenna as the transmitting antenna and the second antenna as the receiving antenna. The first case, assume antenna 1 A1 as the transmitting antenna and antenna 2 as the receiving antenna. Okay. At the same time, assume antenna 1 as isotropic also. Isotropic antenna. About isotropic antenna. Isotropic antenna radiates equally in all directions. Okay. Now we'll see total transmitted power by the transmitting antenna. The total transmitted power is PT. Okay. And the radiated power density. The radiated power density as take it as W naught. W naught is related with the transmitted power as PT by 4 pi r square. You know the power density. The power density is power by area. Okay. Here as the antenna 1 is isotropic, it radiates equally in all directions. Means if you consider the radiation pattern, it is like sphere. So as area, you have to consider the area of sphere. So this is your 4 pi r square is area of sphere. So the radiated power density W naught is equal to transmitted power by area. Okay. Now the directivity dt of the transmitting antenna. Assume this transmitting antenna is having the directivity dt and maximum effective aperture ATM. Same way for the receiving antenna, the first case, assume the directivity as dr and ARM is its maximum effective aperture and the two antennas are separated by the distance r. Okay. Now the directivity dt, the general formula of directivity dt is actual power density divided by power density of isotropic radiator. Okay. Therefore, dt is, what is the actual power density? Actual power density is represented with Wt and the power density of isotropic radiator is represented by W naught. That is this W naught. Okay. So it implies the actual power density Wt is equal to W naught into dt. Now simply substitute W naught from the above expression Pt by 4 pi r square into dt. Therefore, Wt is Pt by 4 pi r square into dt. Now, we'll move to the power collected or received by the receiving antenna is equal to, that is PR is equal to effective aperture of the receiving antenna into transmitted power density. In the last video, I explained about effective aperture. Effective aperture relates with the power. If the effective aperture is more, the power received by the receiving antenna is more. So this is the expression of the power received. Here also the power received is effective aperture of the receiving antenna into transmitted power density. So that is What is the effective aperture of the receiving antenna? AR, and the transmitted power density is WT. Okay. So now it implies PR is equal to AR into, substitute WT, PT by 4 pi R square into DT. It implies DT into AR is equal to PR by PT into 4 pi R square. Okay. So take this expression. And now, in the second case, we will assume antenna 2 as the transmitting antenna and antenna 1 as receiving antenna. We'll see all the above expressions once. For this case, is what is our first expression? The first expression is total transmitted power. The total transmitted power, whatever may be the antenna, the total transmitted power is represented with PT. Okay, then the radiated power density. Radiated power density is W naught, that is PT by 4 pi R square. So in this case, you have to assume the antenna 2 as the isotropic antenna. Remember. Okay, then the directivity. The transmitting antenna directivity. Here the transmitting antenna is the antenna 2. Antenna 2 directivity is DR. You should not change this. I'll show. You should not change these terms ATM, DT and ARM, DR. Okay. We should not change. You must take, in one case you must take antenna 1 as transmitting antenna and antenna 2 as receiving antenna. The second case, antenna 2 as transmitting and antenna 1 as receiving. That's all. You should not change the values. Okay. So in that case, what is the directivity of antenna 2? Antenna 2's directivity is DR. So what is DR? Same. Actual power density. Power density of isotropic radiator. What is that here? It is the power density of the isotropic radiator because it is the total power transmitted by the sphere radius. Okay. Only the isotropic radiator's radiation is in the form of sphere. So actual power density is WT and the power density of isotropic radiator is W naught. So it implies WT is equal to DR into W naught, that is PT by 4 pi R square into DR. We will go for the power received. Which is receiving the power? Antenna 1 is receiving the power. You have to remember. The power received by the antenna 1 is its effective aperture and the transmitted power density. What is its effective aperture? 80. What is the power density? Transmitted power density is WT. So it is 80 into PT by 4 pi R square into DR. Okay. It implies DR80 is equal to PR by PT into 4 pi R square. Here we have an expression. Let it be equation number 1. If you see this expression, let be equation number 2. If you observe the equation number 1, dt AR is equal to PR by PT into 4 pi R square. And if you observe equation number 2, DR AD is equal to PR by PT into 4 pi R square. Okay. So both the equations RHS are same. So you can equate equation number 1 and number 2. So equate 1 and 2. So if you equate 1 and 2 as both the equations are same, what you're going to get? You're going to get dt into AR is equal to DR into AT. Okay, it implies dt by AT is equal to dr by AR. This is the good and biggest relation between the effective aperture and the directivity. Okay. It means always D by A is constant. Always it is constant means if you increase the directivity, or if the directivity of the antenna is increased, or if the antenna is having higher directivity, automatically its area is also high. Or I can say if the antenna aperture is high, then the directivity of the antenna is high. If the directivity of the antenna is high, the power received by the antenna is high. Okay, I'll extend this. Let us write the same expression for maximum cases. DOT by, now we'll write the maximum effective aperture of the transmitting antenna. DOT by ATM is equal to DOR by ARM. Okay, DOT and DOR are maximum directivities. These two are maximum directivities. These two are maximum effective apertures of the transmitting and receiving antennas respectively. Now assume A1 as isotropic. This is to get one good relation. So if A1 is isotropic, what about DOT? But in the analysis part, from the first case we considered antenna 1 as isotropic antenna, and in the second case we'll consider antenna 2 as isotropic, remember. Okay. But in this extension of analysis, I'll consider A1 as isotropic. So DOT is 1. It implies 1 by ATM is equal to DOR by ARM. So totally ATM is ARM by DOR. What is its meaning? Maximum effective aperture of the isotropic radiator or isotropic antenna. We considered A1 as isotropic. Therefore, maximum effective aperture of the isotropic radiator is maximum effective aperture of some other antenna divided by its directivity. So, what is the meaning here? In this case, we consider two antennas. One is for transmitting, another one is for receiving. Okay. So, if one antenna is isotropic, then its effective aperture is the effective aperture of the maximum effective aperture of the other antenna divided by the maximum directivity of other antenna. That is the meaning of this expression. Okay. Now, the special case for very short dipole, you know about the dipole antenna, where for very short dipole means the length is very less than lambda. The effective aperture, maximum effective aperture is 0.119 lambda square and the directivity is 1.5. Okay. If you substitute these two into this expression, so you're going to get ATM is equal to 0.119 lambda square by 1.5. So you're going to get lambda square by 4 pi. So ATM is lambda square by 4 pi for short dipole. So this is general case. Very short dipole is the general case. Very short dipole, you can consider it as a point, as it is having very length. So point source means here is the isotropic radiator. So now you can equate this and this. So you'll get ARM by DOR is equal to lambda square by 4 pi. It implies ARM is equal to lambda square by 4 pi into DOR. So this is the relation between, for our analysis, this is the relation between maximum effective aperture of the receiving antenna and the directivity of the receiving antenna. Use this expression in general. Okay, so in general, we can write, what is this? AEM, maximum effective aperture, as AEM is equal to lambda square by 4 pi into D naught. AEM is maximum effective aperture, D naught is maximum directivity. Okay, this is the exact relation between effective aperture and directivity. Okay. That's all. Okay, thank you very much.